Hey guys. All right, our next topics. Let's get ready. So we're going to be talking about reactions, concentrations, and stoichiometry. So reactions, chemical reactions. We deal with these a lot. When we deal with chemical reactions, we need to make sure that a couple of things have happened. So when we balance a chemical equation, we need to make sure that we have the same number of atoms on both sides and the same charge. Okay, so when we talk about Mg2 plus 2OH minus, it goes to MgOH2, we get 2OH minus because of the 2 plus charge. So that gives us this reaction right here. Now, when we talk about doing, so the first thing we need to think about, all right, is how do we get our balancing for this stuff, the molecules that are present. All right. So we can talk about reactions like, let's see, we'll make stuff up. Magnesium phosphate. Magnesium phosphate plus sodium hydroxide. And that's going to give me a sodium phosphate and a magnesium hydroxide. I'm just going to truncate it there. Okay, so magnesium phosphate. Now, let's look at magnesium. Where did I put the thing? Hold on, I'm missing my periodic table. Okay, so magnesium. And I'm going to pull this over here because we're working on our piece of paper. So magnesium is right here. He's an alkaline earth metal. So I would expect him to have a 2 plus charge. So it's an Mg2 plus. Now a phosphate is a polyatomic ion. He happens to be a PO4 3 minus. So when I put those two together, I have to make the overall charge a 6. So I have Mg3, so we have 3 times the 2 plus, that gives me a total of 6 plus. And then I have a PO4, and then 3 minus times 2 of them gives me a total of 6 minus. So that thing is now net neutral because I have 6 plus and 6 minus. Okay. I add to that a sodium hydroxide. Na is an alkali metal, so he's an Na plus. And hydroxide is an OH minus. That's a polyatomic ion. That's an OH minus, and that gives me an NaOH because those two come together that way. Now, when we go to the other side, we take the cation from the first one, so the Mg that's here, and react it with the anion from the second one. So it's going to be an MgOH. So that's magnesium hydroxide. Now, remember, this is an Mg2 plus, and we're going to have an OH minus. So in order to make that work, I have to have an MgOH2. We're also looking at the cation from the second thing, so the Na plus, reacting with the phosphate, so the anion from the first thing. So those are the two things that I'm looking for at there. In order to make that work, I have to have an Na3 and a PO4. So cross multiplying, the 3 negative charge becomes the subscript on the Na, and the 1 charge on the Na becomes the subscript on the PO4. Okay, now once I have balanced those for charge and I've made those molecules that are neutral, I can't change those subscripts again. All right, that is not something that I can do. So when I go to balance this thing, I have to know Mg, PO4, Na, and OH. And while I understand that PO4 can technically come apart, the majority of the equations that you will see at this point will not have that happen. So if we keep the ion together, then we're in a better place. Now, right now, what I'm going to do is indicate how many of each thing I have. So I have 3 Mgs over here, and I have 2 phosphates on the reactant side. I have 1 Na and 1 OH. And I'm also going to look at charge. I have no charge on that side of the equation. When I look at my products, I have 1 Mg, I have 2 OH, I have 3 Na, and I have 1 PO4. That's not balanced. And my charge is 0, but that's not balanced. I don't have the same number of things on both sides. So if I need to fix the Mg, because that's the first thing I wrote, if I have 3 of them on the reactant side and 1 on the product side, I can multiply this Mg by 3. That gives me 3 Mg, but that also changes my OH, which was 2, to now be 6. Okay, so I messed up the OH. Awesome. So if I look at that, and I know that I have 6 OH on the product side, then I'm going to change this to be a 6 on the front of the Na. So that means I now have 6 Na and 6 OH. So Mg is happy, and I have a happy OH. But I don't have an happy Na, so I have 6 on the reactant side, but only 3 on the product side. So I can multiply this by 2. If I do that, then that fixes my Na. And now I have, again, because I've done that, that changed my PO4 to 2. And now I have the same number of things on both sides and the same charge on both sides. So that's how I balance my equation. Now, is it necessary to do this balance sheet like this? No, absolutely not. But that's how I do it, okay? So I always start by knowing what those charges are, figuring out how to make the molecules. So if I were writing this, this would be a net ionic equation. This would then be a molecular equation, or sorry, this is an ionic, this is a molecular. And then I make sure that everything is balanced with this, okay? So that's how I handle that. Those are our chemical reactions. Now again, the majority of the chemical reactions we will deal with are double displacement. So the cation from this one goes with the anion from that one, and the anion from this one goes with the cation from that one. If we're going to do anything more complicated than that, you will probably be told what it is you have. So I said here that we made sodium phosphate and magnesium hydroxide. I could specify that we make water and CO2 and something else, and then we would indicate that we have all of those things and balance for them. Okay, so that's how we're going to deal with that. All right, make sure that you have the same number of both things, mass balance on both sides, and the same charge on both sides. Now, your charge may not always be 0, okay, but we need to make sure it's the same on both sides. So that's how we deal with our reactions. And when we talk about our chemical reactions, one of the other things that we often talk about when we're dealing with chemistry is concentrations. Okay, the most common concentration that we use is molarity. That's this one right here. So molarity is equal to moles of solute over the liters of solution, and it's symbolized by big M. This is easy to measure. It's easy for us to talk about. It's the most common thing for us to deal with, and that's a concentration like we talked about in KC. Now, are there other things that we can use? Absolutely. We can talk about molality, and remember, molality is moles of solute over kilogram of solvent. It's symbolized by little m, and we use molality in times when it is changing temperature. Okay, so if my temperature is changing, the volume of my solution is going to change. So I can't use a molarity. I have to use something that's independent of that volume. So molality is used when we're talking about changing temperatures. So things like boiling point elevation, freezing point depression, all of our colligative properties tend to use molality. We can talk about percent by mass, which is the mass of our solute over the mass of the solution times 100. We can use that. That is something that we are given. Sometimes, it tends to be an old school way to do this, but we sometimes get things that we've purchased that come in a percent by mass. That's usually the only way that we do that. All right, it is independent of temperature, but that's usually what we're dealing with that. Now, there's another thing, and that's the mole fraction. Now, the mole fraction for a component of A is called chi. Chi A is equal to the moles of A over this total number of moles. And where would I use something like that? Well, chi is used when we talk about partials. Okay, so if I want to know the pressure of like N2, then I can multiply that by the total pressure. So chi of N2 times the total pressure, we're giving the pressure just of N2. So that partial part is due to how much of that thing is due to the nitrogen. So we need to know that kind of thing. Okay, so that's where we deal with those. Partial pressures of gases, when we talk about vapor pressures, that's when we'll need those mole fractions. Now, should you be able to convert between any of these? Yes, you should. Okay, that is an exercise you should be able to do. And that's based on these definitions. So mass of solute over mass of solution, moles of solute over liters of solution, moles of solute over kilograms of solvent, and moles of A over the sum of all the moles. So you should be able to convert in between them. We should be able to get any of the numbers that we need. There are some practice problems that I've given you here for calculation concentrations. I'll let you look these over because we go get the molarity, we then do the molality, we do the percent by mass, and then we do the mole fraction for those. So I'll let you look those over. It's really important that you remember what the definitions are for these things, just in case you're given one. Now, if you don't remember, right, and you can get a hold of me on a test, then you can ask me about it. Okay, I do not put those definitions in there, and that's because the handouts I use for 111 are the same as I use for 110, and I want them to know what those definitions are in 110. So it's important that you be able to look them up in the real world. All right. So if you have a unit that you don't really know how to deal with when you're taking a test, if you can't get a hold of me to get a definition for it, then you need to tell me that I don't know what the units are for this, but here's what I think I should do. Okay. So for instance, if you're given a percent by mass and you can't remember if that percent by mass is the mass of the solute over the total mass or the mass of the solute over one of the other components or whatever, you need to tell me what you think it is, do the calculation for what you think it is, and then we'll look at it from there. Why do I say that? Because it's important to me that you know what to do with what you have. Not that you got that definition right. There'll be a point or two taken off for that because it's not correct. I mean, it's not 100% correct. But if you do the right thing with the wrong definition, then you've gotten me to see what I needed to see. You know what to do. So make sure that you work with that if that's what you come up with. Okay? Now, stoichiometry. Oh, stoichiometry is one of my favorite things. Stoichiometry is a fancy word for how we talk about how much of something we have. So we can talk about how much of something we have. So the mass of sodium hydroxide that we were given. Then we want to talk about the number of moles of sodium hydroxide that is. And I'm going to make this bigger just so you can see this. Now, this diagram is actually in your handouts. And you'll see that we have grams of A. We can convert that to moles of A by using the molar mass. Okay. Now, it's up to you to figure out whether I need to multiply or divide. That's for you. We can get from moles of A to the volume of a solution for the gas, okay? And we do that using the molar volume, all right? We can get to the number of particles by using Avogadro's number. I can get to the molarity by dividing by the volume of that solution. And of course, if I have grams of A and I want to know what the volume of A is, if I know the density, I can get there. Now, once I can figure out all of these things about A based on the conversions in between them, we usually want to talk about how do we get from something in measuring A to something in measuring B, whether that be another reactant or a product. Okay, and we can do that by using the stoichiometric coefficient, the factor that comes from that balanced chemical equation. So that has to be included. Okay. Now, once we get to moles of B, we can go to the grams of B, the volume of B, whether that be a solid or a liquid. We can go to the number of particles of B, or I can go to the volume in actually solid, liquid, or gas, depending on what things I know. Okay. So that's what our stoichiometry is based on. And again, this image is present for you on the test. And that's because I don't expect you necessarily to know how to get between everything, but it may help you to remember how to get there based on what you have. So figure out where you have and where you need to go and what it's going to take to get you between the two. All right. Now here's an example. Silver iodide reacts with iron 3 carbonate to produce iron 3 iodide and silver chromate. 12.34 grams of iron 3 carbonate and 26.574 grams of silver iodide are added to 1 liter of water. What amount of silver chromate is produced in terms of moles, molecules, and grams? Okay. So my problem solving comes in. I have iron 3 carbonate. So carbonate is a CO3 2 minus, and Fe is a 3 plus. So I have Fe2CO3, okay, to balance for charge. I know that I have 12.334 grams of that. I have looked up the molecular weight, which is 291.72 grams per mole. I know that I'm going to add AgI to that, so silver iodide. Silver iodide. And there's 26.574 grams of silver iodide. Its molecular weight is 234.77. I want to know how much AgCO3 I make. And it's Ag2CO3 because it's an Ag plus and a CO3 2 minus, so it's an Ag2CO3. I know the molecular weight of the Ag2CO3 is 275.75, and I don't know how much of that I have. I also know that I have an FeI3, so iron 3 iodide. Its molecular weight is 436.56 grams per mole. And then I can balance this equation. So once I've written the molecules that go into it, I can balance it. I have 2 irons here, so I need 2 irons there. I have 2 irons there, that gives me 6 I's. So I need to multiply by 6 over here, that gives me 6 A's. I had 2, so I multiply this by 3, and then that means that I have 3 CO3 and 3 CO3. So everything is mass balanced. I don't have any charge anywhere, so I'm also charge balanced. So whew, I have taken care of that. Now, this is a limiting reagent problem, okay? And I am looking to do this, and I did this solely for the iron. Now, should I have done it for both? Absolutely, I should, but I didn't. So at this point, I do 12.334 grams of iron 3 carbonate. I divide that by the molecular weight to get the number of moles of iron 3 carbonate. I use the molar ratio. 1 mole of Fe2CO3 3 makes 3 moles of Ag2CO3, and that tells me how many moles of Ag2CO3 I make. I can do a conversion that's exactly the same but has one additional step where I multiply by the molecular weight of the Ag2CO3, and that tells me how many grams of that material I make. I can also, once I get to the moles, I can multiply by Avogadro's number to tell me how many particles I have. And of course, that's molecules because it's an Ag2CO3. And you can just call it particles. You can call it molecules. It's not an ion, so I wouldn't call it that. Any word that works for it is okay. All right. Now, should I have done this with the 26.574? Absolutely. I should have exactly the same things for that 6.574 grams of silver iodide, and whichever produces less, that's my limiting reagent. Okay, I did not do that so that you could go home and do it, and I can put up the answer to the 26.574 grams of AgI to D2L so that you can try it and then you can verify. Okay, again, we want that in moles, grams, and number of molecules. So that's my stoichiometry example. Go stoichiometry. That's awesome. All right. So we've now talked about reactions, concentrations, and stoichiometry. We're going to take another break. I'm going to stop this video, and I will get ready for the next one. All right.